Hello, this is my Physics 2211 Lab 1 video on constant velocity motion. So, quick overview of this lab. The scenario we're looking at is tracking motion of an object with constant velocity. The main fundamental principle that we are focusing on is Newton's second law, or the momentum principle, shown here as the net force, being equivalent to the change in momentum of a system over its change in time. So electronic tools used were a tracker to track the motion of an object, glow script to create the model, and a recording camera. So a few important starting equations and definitions. Momentum is defined as the product of a system's velocity and its mass. So with momentum and velocity being vectors and mass being a scalar. This is a definition of average velocity. It's displacement, or final position minus initial position, over a time period. And with a bit of algebra, we can isolate the final position of a system to create the position update formula shown here, which we will see later. So Newton's second law is extremely powerful because it relates the rate of change of a system's velocity over a certain time interval to the ratio of the total net force acting on the system to the system's mass. Now it's important to note that this is the total net force, not individual pushes or pulls on the system. We cannot isolate individual ones, we just know the total net force, which is still extremely powerful. So with a bit of algebra, a few important implications can be concluded. This is the velocity update formula. You can isolate the final velocity from the delta V and create this nice formula to find the final velocity of a system over some time period. And the momentum principle, additionally, using the definition of momentum as we discussed earlier. So the goal of this lab is to use Newton's second law to create a computer model and predict the observed motion of an object at a constant velocity. So let's take a quick look at the video capturing motion now. A few notes on it is the system is the tennis ball, the surroundings is everything else in the room and the universe. Orientation is the positive x-axis to the right, positive y-axis to the top, and we'll see if the orientation would matter. Calibrated to the diameter of the tennis ball, and the frame rate was 24 frames per second. So here's the model. The orientation is these axes, and that is the distance. That was the motion of the ball, created a position versus time graph. Data points here. So a different orientation of the axes would not matter. It would only change the look of the graph, because the position data would then be negated in a different way, and it would just reflect either over the x or the y axis, depending on how the axes were lined up, but the position data itself would be consistent. So here is a model description for the initial conditions: the mass of the ball, the initial position, the initial velocity, which was found by taking a position right after the initial, about 0.042 seconds after it, and finding that displacement and then dividing it by that delta t to get this initial velocity, and the initial time starts at 0. So this is translated into the code shown here. And the time step is about 0.05. It was decreased a bit to increase the number of data points. So here is the prediction motion of the loop for the code up to the max time it was recorded for. So this is the updating loop, and the net force was set to a 0 vector. And that is because, as we can see from the velocity update formula, if we want the final velocity equal to the initial velocity, because it's a constant velocity motion, since mass and delta t, changed in time, are non-zero constants, the net force would thus have to be a 0 vector. So we put that in the code, and we also put the velocity and position update formulas in the code, as we discussed earlier, and it would advance the clock. And there's also some other modeling stuff. But let's take a look at the model now. So here's the code itself, and we run it. So that would be the tennis ball, and that is the initial position. And we can see a position versus time graph shown here. Now, let's compare it to what we got from the model. So the model data is a perfect linear line, and experimental data is pretty close, but it's not exactly the same. There are a few reasons why, potentially. First one would be me, because I'm not perfect at choosing positional data and tracker. The nonlinear motion of the tennis ball could actually be moving in backwards a bit, so that would change the observed position in the video. The orientation of the camera could not be perfectly perpendicular to the motion, and possibly the slowing down near the end of the video could change the end of the graph as shown. So that is Lab 1. Thank you for watching.